About 4.6 billion years ago, within the Orion arm of the Milky Way galaxy, a star was born. At first, it was surrounded by a cloud-like protoplanetary disk that consisted of dense gas and dust. This star was our Sun. And this is how our solar system looked before the planets emerged. The mineral grains within the protoplanetary cloud began to accumulate, forming larger and larger chunks of rocky matter, starting the process known as accretion. As the rocky chunks grew larger, they attracted more and more of the smaller matter, forming the first asteroids. Until recently, it was thought that these asteroids collided with each other, slowly growing to form planetesimals and protoplanets. The problem with this theory was that modern computer modeling indicated that, rather than leading to growth, these collisions would probably have resulted in the destruction of the asteroids. In 2019, the New Horizons probe flew by a strangely shaped object at the edge of our solar system in a region known as the Kuiper Belt. This object, named Arrokoth, consists of two lobes connected by a thin neck. Instead of being formed by a collision, Arrokoth's shape tells a story of two separate objects orbiting each other in synchronicity until slowly coming together and merging. This discovery points to a different hypothesis, known as gentle clumping, in which orbiting material formed into clouds that gradually collapsed into themselves. Over time, this clumping created the planetesimals and protoplanets, from which actual planets would eventually be formed. One of these planets was Earth. Many astronomers believe that after millions of years of asteroid bombardment, Earth was struck by an object about the size of Mars, in what is known as the giant impact hypothesis, or the Theia impact. This cataclysmic event generated enough heat to liquefy Earth's surface and turn it into a vast ocean of molten magma. But something else was happening that would literally change the destiny of our planet. Most of the material that was blown into space after the massive impact remained within Earth's orbit. And once again, the process of accretion began. Increasingly larger-sized chunks of material joined together and formed a new orbiting satellite, our Moon. When this new heavenly body rose above Earth's horizon, it would have been a spectacular sight. It was geologically active and almost 16 times closer to Earth than it is today. Although the giant impact hypothesis of the Moon's formation is perhaps not an obvious model, it is the most widely accepted explanation today. Let's have a look at how scientists came to this extraordinary conclusion, and why they think our heavenly companion was born from a cataclysmic event. At one point, there were three dominating theories to explain the formation of the Moon. The first one, called fission theory, was proposed by the son of the famous British naturalist Charles Darwin, George Howard Darwin, in 1878. It stated that upon formation, the molten Earth was rotating around its axis so fast that an enormous chunk of lava was ripped from its surface and started orbiting our planet as an independent satellite. The basin of the Pacific Ocean was believed to be the scar that remained after Earth gave birth to the Moon. Another explanation for our Moon's appearance is called the capture theory. It suggests that the Moon was initially an independent planetesimal that formed not far from Earth when the solar system was born. At some point, these two bodies passed at a very close distance from each other, and Earth, being a larger object, captured the Moon, shifted it from its orbit, and gradually tied it to itself. Finally, there was the third hypothesis that explained the moon's formation, called the co-formation theory. According to this model, the moon was assembled roughly at its present location out of the unused leftover rocks and dust that remained after Earth's formation. This model seemed plausible because this is how the planets of our solar system formed around the Sun. Moreover, the satellites of the gas giants like Jupiter and Saturn were born this way. But there was no way to prove or disprove any of these theories without actually getting to the moon and analyzing the soil. Our science took a giant leap forward in the second half of the 20th century with the beginning of the space exploration era. On the 21st of July, 1969, the Apollo 11 module landed the first people on the moon. They collected 21.5 kilograms of lunar material and brought it back to Earth 3 days later. Since then, almost 400 kilograms of lunar soil have been retrieved from the moon, more than enough material for scientists to analyze. But what did the analysis of the lunar samples tell us? First of all, it demonstrated that although the minerals from the moon were generally similar to those on Earth, they were quite different when studied in detail. Second, the density of the moon turned out to be much less than the density of Earth. Scientists also found out that lunar rocks are almost devoid of nitrogen, sulfur, and hydrogen, the volatile elements that evaporate first if heated. In addition, water was not found in the samples of lunar material. The moon turned out to be very dry. This meant that the surface of the moon was heated and baked at some point, purging it of all of its volatiles. Another important discovery showed that the proportion of oxygen isotopes from the moon is similar to that of earthly oxygen. This meant that the moon and Earth formed roughly at the same distance from the Sun. Being armed with this new data, scientists were able to re-evaluate the existing theories of the moon's formation and determine which model worked best. Let's take a look at the fission hypothesis proposed by George Howard Darwin. It looks convincing and explains chemical similarities between Earth and the moon, as well as the fact that the moon is always facing Earth. But this theory doesn't answer the question, where did all the volatiles go from the moon? In addition, computer modeling results reveal that a moon-sized chunk of molten lava could only have been ejected from Earth if it had been spinning incredibly fast, about 1 rotation per hour. The Earth-Moon system just doesn't have that kind of rotational inertia, so the fission theory was dismissed. The capture theory implies that the moon was formed close to Earth, and, therefore, should be almost identical in its chemical composition. The analysis of the lunar material showed that the moon is not identical to our planet. If the moon happens to form in a part of the protoplanetary disk far from Earth, that would explain the difference in composition. But calculations and computer modeling tell us that the moon would have passed at a very high orbital speed in relation to Earth, and Earth would not have been able to capture it. So the capture theory was no longer a contender. The co-formation theory also fails to explain the differences in the composition of Earth and the moon. If both objects had been formed from a common protoplanetary clot, they should have been chemically identical. But they are not. This theory, too, was dismissed. With none of the 3 main theories of the moon's formation being correct, scientists needed a new explanation, one that would accommodate all of the available data and resolve the contradictions of the old hypotheses. In the 1970s, a new hypothesis of the moon's formation started to take shape in the scientific community and became known as the giant impact theory. It went like this. In the early days of the solar system, 2 planets, larger Earth and smaller Theia, existed at the same distance from the Sun. We know that 2 planets cannot coexist in one orbit and will eventually collide. When this happens, the smaller planet is doomed, and the larger one survives. The inevitable collision between the two planets happened around 4.5 billion years ago, when Theia hit Earth at an acute angle. A huge amount of molten rock and heated gases were ejected into space and accumulated within Earth's orbit. And with time, the accretion process led to the formation of a new heavenly body, just over 24,000 kilometers from Earth. In essence, Theia died, giving birth to the moon we still see today. The volatiles like sulfur, nitrogen, and hydrogen escaped during tremendous heating at the time of the impact. This is why they are absent from the moon. The absence of iron on the moon is explained by the fact that almost all of Theia's iron was consumed by Earth. The moon is always facing us with one side, because the moment of inertia of Earth and Theia combined in a single orbital system. It is also likely that Earth's 23.5-degree axial tilt is a result of the giant impact. Of course, we will never find absolute proof of Theia's existence, and it will forever remain hypothetical. But both computer modeling and data from the lunar soil fit with the giant impact hypothesis quite well. Meanwhile, as Earth was recovering from the tremendous impact, its surface started to cool and harden. It began to form an atmosphere of carbon dioxide, carbon monoxide, water, hydrochloric acid, sulfur, nitrogen, and methane that had been outgassed by the destruction of the mantle and the subsequent volcanoes. Although this major catastrophe was now over, Earth remained a hostile place. It was a realm of volcanic terrains, hot, dry, and barren, with a dense high-pressure atmosphere of deadly gases. This time in Earth's history is aptly called the Hadean Eon, named after Hades, the ancient god of the underworld. It was also a time of intense geological activity, with countless volcanic eruptions. About 100 million years after the giant impact event, Earth had cooled down sufficiently for water released into the atmosphere to obtain the state of vapor, and the very first clouds began to form in the atmosphere. These water clouds increased Earth's albedo, causing more solar energy to reflect back into space, and allowing the planet to cool off even further. Eventually, water was able to exist in its liquid form. Although the temperature on Earth was still above 100 degrees Celsius, the water did not evaporate because the atmospheric pressure was much higher than it is today. This allowed the water droplets to form and head down to the ground in such hot conditions. And this is how the first rain in our planet's history began. It lasted for thousands of years, gradually covering Earth's surface with water, forming the first ponds and lakes and the first seas. Until the entire planet was covered with water, turning it into an ocean world, enveloped in a reddish methane mist. There was no dry land at the end of the Hadean Eon, the first chapter in our world's history 4 billion years ago. Water is essential to life. It covers 70% of Earth's surface, and it accounts for 60% of the human body. Without it, we simply would not exist. But where did this critical compound come from? For a long time, scientists have understood that even if Earth had contained water upon its formation 4.6 billion years ago, the planet was so hot that it would simply have boiled off. But we also know that there was liquid water on the surface of Earth at least 4.1 billion years ago. So how did it get here? One explanation was that once our planet had cooled off sufficiently to sustain water in liquid form, it was brought here by comets and meteorites. We know that comets consist of ice, which is frozen water. We also have evidence that our planet was bombarded by comets over the course of millions of years. Therefore, the simplest explanation seemed to be that ice was delivered here by comets and meteorites, and that when it melted, it filled the ocean basins with water. So, that was the answer. Or was it? In order to verify this hypothesis, scientists endeavored to determine whether the water carried by comets was similar to the water here on Earth. What does that mean? Water is water, and H2O is a universal formula for it. So how could one form of H2O be different from another? It turns out that water is different in different parts of our solar system, and here's how. As we know, hydrogen is part of the water molecule, but sometimes hydrogen receives an additional neutron. When it does, this hydrogen atom is called heavy hydrogen, or deuterium. Our earthly water has a certain proportion of deuterium and hydrogen atoms, known as the DH ratio, which is 1.55 parts per million. As a comparison, the DH ratio of Martian water is 300 parts per million, so we know that it's different from ours. In 1986, when the Giotto probe reached Halley's Comet, scientists measured the DH ratio in its water and compared it to the water here on Earth. The two didn't match. In fact, the DH ratio of the water on Halley's Comet was twice that of ours. After analyzing the water on Halley's Comet, we started to measure the DH ratio in every additional comet we could reach, mainly remotely, using telescopes. When we examined the data from 5 more comets, not one was found to be a match. But there was still hope. Until recently, it had only been possible to measure the DH ratio in comets that came from the Oort cloud on the distant periphery of our solar system. But there is another group of comets out there, called Jupiter family comets. They reside between the Sun and Jupiter and have short orbital periods of 20 years or less. Because of their proximity to the Sun, they are exposed to significant solar radiation, and by now have lost most of their volatiles. For this reason, they're no longer very bright and are extremely hard to measure remotely. But in 2010, scientists managed to measure the DH ratio of Hartley 2, a comet belonging to the Jupiter family, and they found an exact match to the ratio of water on Earth. It seemed likely, after all, that the Jupiter family comets were responsible for bringing water to Earth. But it never hurts to double-check, so they did. In 2014, the famous Rosetta spacecraft reached the Churyumov-Gerasimenko comet from the Jupiter family and analyzed its water. This time, the DH ratio did not match, which indicated that the comets in our solar system were too diverse in their composition and probably were not the unique source of water on ancient Earth. So where did water come from? After comets proved to be poor candidates, scientists looked to the great quantity of asteroids that orbit the Sun between Mars and Jupiter and form the asteroid belt. They contain water today, and are believed to have contained even more water back when the solar system was being formed. Moreover, the DH ratio of the asteroid's water is quite close to that of our planet. The mystery seemed to have been solved once again, and articles filled the internet with headlines such as "Water brought to Earth by asteroids, not comets." This new hypothesis proposed that asteroids struck Earth, delivering a new layer of material to its surface that contained precious metals, along with carbon, and crucially, water. This layer was called the late veneer. However, recent studies have shown that some of those precious metals on Earth have different atomic signatures than the ones originating in the asteroid belt, casting doubt on the hypothesis. In addition, the timing just doesn't work. The late veneer was thought to have been delivered during the late heavy bombardment 3.8 billion years ago. But today we know that our planet was already filled with oceans at least 4.1 billion years ago. This means that the asteroids could not have been the source of our water. So what was? Apparently, its constituents have always been here, on Earth, since the start of our planet's formation. Not on the surface, obviously, but deep in the mantle, where hydrogen and oxygen elements were trapped in the minerals. When these minerals melted, the hydrogen and oxygen dissolved into the magma, forming water, which was released into the atmosphere through volcanic eruptions. When the surface of the planet was cool enough, water started forming clouds, which finally rained down onto the surface of Earth, filling up the oceans. This is the latest thinking on the subject of water's origin on our planet. Things could change in time, though, if further research leads to new discoveries. As Earth was young and extremely active geologically 4 billion years ago, volcanic cones started rising above the water's surface. They formed small volcanic islands and archipelagos, the first bits of land in the endless primordial sea. Over time, erupted lava accumulated more and more around those archipelagos, and the islands grew larger. Gradually, these small islands grew into larger land masses, the first protocontinents. It was the dawn of another geological time, called the Archean Eon, which in ancient Greek means origin or beginning. Although Earth at this time resembled our modern planet more closely than during the previous Hadean Eon, this world was still a hostile and alien place. Indeed, there were familiar elements: oceans and land, winds and rainstorms, clouds and tides. But it remained a place with unbreathable atmosphere, rocky land, and anoxic oceans. As there was no oxygen, our planet did not yet have the protective ozone layer, so its surface was exposed to deadly UV radiation coming from the sun, which incidentally was 25% dimmer than today. At this time, approximately 4 billion years ago, a very important event took place. This occurrence would transform the entire planet, from its geology and atmosphere to its overall appearance, and because of it, Earth would eventually become the familiar place we know today. This event was the emergence of life.